Hello students, a very good morning everyone. Very good morning to everyone. Welcome to session and welcome to Byjus exam prep. And for the GATE 2025, this is a session on an important topic discussion, okay, for electronics and for computer science aspirants. Yes, that is the floating point representation of numbers. Okay, now how to deal, what exactly is the concept of floating point variables, floating point numbers, when do we need them, and what are the conventions, especially what are the IEEE standards for the representation of floating point numbers. All that we are going to discuss that. So I'll tell you, this session will be sufficient, okay, for your concepts and any type of questions that is related to floating point representation of numbers. Yes guys, very good morning everyone. Very good morning. Come on everybody, quickly keep on joining. Yes. All right, dear. Okay, so let's get moving ahead. Let's get started then. Okay, so this is a regular brief intro about me. Must be aware of. So guys, 3rd of April, an important update for all of you. That is the coming Wednesday at 7:30 p.m. on the BYJU'S exam prep app. Okay, Richa ma'am is going to bring you a workshop, Crack Gate 2025, Insider Tips and Techniques. Okay, some more detailed and secrets of success, okay, will be discussed by Richa ma'am on our app on the Wednesday. So if you don't have the app, you can directly download from the Google Play Store. All right guys, and the National Scholarship Test of Byjus is going to be conducted on 14th of April. Yes, the 14th of April, anywhere between 9 a.m. to 9 p.m. you can appear in this National Scholarship Test, and based on your performance, you can get as much as up to 90% scholarships. Okay, this again is available on the Byjus exam prep app as well as web. Okay, you can register now for the event. And GATE 2024 results, were declared, and Byjus exam prep students have outshined, okay, multiple single-digit ranks across multiple branches. Okay, I have 1, I have 2, 4, etc. And more than 30 students securing rank under 100. Right, very good morning, Bhanu Teja. Good morning, Ramji. Okay, ji. Okay, so now, what exactly is this floating point? Why do we need them? And what is the representation of this floating point? Let's learn about that completely. Yeah, let's learn about that completely. Very good morning everyone. Okay, so specifically when we are dealing with very large or very small values, okay, what could be that order? I'll give you an example. Okay, yeah, so dealing with very large or very small numbers, a more flexible representation, like normally we have the 1s and 2s complement representation, but here we're going to talk about another representation, floating point representation, that can be employed. So I'm telling you something which could be very large. Okay, so say for example, sign could be anything. Okay, you may have a number plus minus 8.26 into 10. Let's start with the decimal. Of course, we are going to represent in binary. Ultimately, it's in binary only. Into 10 raised to the power 61, suppose. Now, see, imagine how big this number is. Okay, 8.26, 10 ki power 61. Okay, 10 ki power 61. Now, this is a number system having what base? This is the base 10 case. Okay, or the number could be even very small, not only very large. Okay, for very small or for very large number. Suppose I give you plus 2.89 into 10 raised to the power minus 50. 10 raised to the power minus 50. Now see, 10 power minus 50, how many decimal places will come? 0. The number would be something like 0.00000000000000000. You can understand how small the number is going to be. How small the number is going to be, right? So, okay, for larger or for very smaller numbers, okay, we are going to use the floating point representation. Okay, now, here the base is 10. So what is the representation coming up here is, okay, there is some number which could be fractional in nature. Okay, it could be positive, it could be negative. Okay, but the representation is fractional part into 10 raised to the power what? Into 10 raised to the power some exponent. Then we will come to the standard representation. Okay, right now just keep understanding. Good morning, Ruby. Okay, right now just keep understanding this much. Okay, so like here it was R10. Acha. In general, what it is going to be? in general, it is going to be any fractional part into base r, okay, into whatever could be the base r raised to the power e, okay, where r is the radix or the base of the number system. R is the radix or the base of the number system. Okay, so say for example, if you are dealing with binary r equal to 2, the such representations will be looking like f into 2 raised to the power e. That is going to look like what? F into 2 raised to the power e, right? Okay. Now the problem is, because you are writing it into a fractional part into 10 या into 2 power something, the problem is what? That the representation will not be unique. Now what is that I mean by unique? Okay, what is that I mean by unique? Now let me take some smaller number. Suppose I take a number 642.59. 642.59. This is a fractional number. Now in how many ways I can represent this? Okay, this is one way directly. This is one way directly. Okay, this can be written as 642.59 into 10 raised to the power 0. If I have to write it into 10 power e, so it is into 10 power 0, the number itself. We could also write it as divide by 10 and multiply by 10. So 64.259 into 10 raised to the power 1. That is also clear to everybody. Okay. We can even also write it as 6.4259 into 10 raised to the power 2 into 10 raised to the power 2. Not only this, we can also write it as multiply and then divide by 10. So we can write it as how much? We can write it as 6425.9 into 10 raised to the power minus 1 into 10 raised to the power minus 1. ठीक है, या into 10 power 3 का केस भी ले सकते थे, 0.64259 10 power 3. So point is कि when you are representing it as fractional into 10 power exponent, okay, the representation is not unique. The representation is not unique. There can be multiple ways of representing, right or wrong? Any doubt, please keep asking me. Okay, so there can be multiple ways of representing, ठीक है, and etc, etc, etc. The list is big. So that is why now this calls a need for a standardization, a normalization. Okay, so we now define a concept of normalized fraction. Because what I am telling you, how is the representation looking like? Just a second. Yeah, sorry, all okay. What I am telling you, how is the representation looking like? The representation is fractional part into r power e, or decimal mein 10 power e. Okay, so there can be multiple ways of writing it into 10 power something, into 10 power something. There are multiple ways of doing it, right? So what is the normalized fraction? What is the meaning of this normalized fraction? That I allow only one non-zero digit before the point, before the decimal point, or before the radix point, whatever the base could be. Okay, we allow only one non-zero digit, okay, before the decimal point. Here, let me in general write it as before the radix point. Before the radix point. What does that mean is, if I take the previous example, 642.59, 642.59, there are multiple ways of writing, but this is what I am going to choose actually. Because look into this. This is my decimal point. This is my radix point. Before that, only one non-zero digit should be there. Before that, only one non-zero digit should be there. Okay, so 6.4259. Okay, so this is equivalent to, okay, 6.4259 into 10 raised to the power kitna hua? Into 10 power 2. Now whatever is the exponent coming up, that will be my final exponent. The fractional part is 6.4259 into r power into 10 power e, where the exponent part is equal to 2. Okay. But now, okay, this is one standardization. Okay, I have normalized it. Okay, but now 6.4259 in different fractions. In different fraction, there are different fractional part. Pehle to maine bola how many digits will be there before the fractional point. Okay, how many will be there before the fractional points? Okay. So I told you, let's take only one digit before the fractional point. Similarly, let us also fix the number of digits. Let us also fix the number of digits after the fractional point. Okay, now this is one representation. What is IEEE representation आएंगे, अभी हम एक अपना representation बना रहे हैं, right? Correct. Good morning, Abhishek Kumar. Let us understand this representation first. Okay, so now what I am telling you next is, let us now have the fixed number of digits after the radix point. Okay, say for example, it could be anything. I'm telling you IEEE में क्या है वो मैं बाद में बताऊंगा, but say for example, okay, let us allow 2 digits after the radix point. Let us allow the 2 digits after the radix point. Okay, so then this number, सबसे पहले मैंने क्या बोला था, 642.59 is written as 6.4259 into 10 raised to the power 2. Number one thing I told you that before the radix point there should be only one digit. Then after the radix point, let us say there are only 2 digits. Okay, so this will be approximated as 6.4259, can be written as 6.43. Yeah, if you want you can write it as 6.42 itself. Okay, 6.42 itself. Approximate nahi bhi karo, 6.42 into 10 power 2. Okay, of course this has a drawback. I mean, drawback kya bolenge, there is something which we have to compromise. Okay, otherwise, you know, in every representation, different number of digits will come after the radix point. But what is the problem here? Okay, there will be loss of precision now. The problem here is this leads to loss of precision. What is the meaning of loss of precision? Okay, when I only write down the number 6.42 into 10 raised to the power 2. Okay, now what is the actual number? Somebody can understand anything, na? Okay, somebody can understand 6.4291 into 10 ki power 2, or somebody can understand 6.4225 into 10 ki power 2. Somebody can understand this as 6.4289 into 10 power 2. Anything could be understood because the rest of the digits are not mentioned. I have taken only 2 digits after the decimal point. So there is a slight loss of precision. I mean the actual number and this approximate number may thora difference aayega, but that's okay. We have to define some convention and that's not going to be big. That's not going to be a big deviation. Okay. So this is what is one thing you must know. Okay. Now this clearly tells you that when you are representing the numbers in floating point, there are 3 different fields. Okay, अभी तक यहाँ पे देखो. Okay, what are the 3 different fields? Number 1, what is the fractional part? Okay, we are going to officially call it as mantissa. Okay, what is the exponent value? What is the exponent value? And number 3rd here is the sign. Number 3rd here is the sign. Okay, the exponent part, the fractional part, the sign. These are the 3 important things that is going to matter in the floating point representation. Clear? That is going to matter in the floating point representation. Let's move ahead. Yeah. So in the floating point representation, you will have the 3 fields. Okay, the sign, the exponent, and the mantissa. We are going to call it as S, E, M. Okay. Now, of course, sign can only take 1 bit. Like in our language, sign are 2 plus minus. Similarly, binary also we know from the 2s complement system. Okay, the sign are only 2 plus minus, so plus is 0, minus is 1. Okay, so we know only 1 bit. We need only 1 bit to represent sign. Okay, if that bit is 0, it's a positive number. If that bit is 1, that's a negative number. That's what we already know. Okay, now how many bits for exponent, how many bits for mantissa? Okay, it could be anything. So we have to define the standard. Let's come to IEEE standard of representation of numbers. Okay, now there are 2 formats. Okay, that is also important, 32-bit and 64-bit. 32-bit and 64-bit. But before now, IEEE format will be for, of course, decimal. Oh, sorry, of course, for binary. Abhi tak main decimal bata raha tha. So if I now take a binary example, okay, suppose I write down any binary number at random 10101101.10110101. Suppose, okay, yeah, itna hi le lete hain. Suppose that is some binary number given to me, a fractional binary number. But as per the rule I told you, okay, there should be only one digit before the radix point. Okay, तो ये radix point को shift करना पड़ेगा. तो this should be equivalent to, okay, radix point को कितना पीछे shift करना है? 1 2 3 4 5 6 7. Okay, so I will write this as 1.01011101, then 101101 into, now radix point is shifted 7 positions before, so this number, now it's a binary number, like decimal was multiplied by 10 power 7 na? If you shift the decimal point 7 places below, that means you have divided by 10 power 7, so you multiply 10 power 7, here it is binary, we multiply by r ki power 7. Okay, now you look into this, what is this known as? Okay, what is this known as? Okay, this is going to be sine. Okay, then there is a exponent part and then there is a mantissa part. ठीक है, sine तो आप यहाँ से भी देख सकते हो. That's not a problem. Okay, so this says that the sine bit will be 1. This says that the exponent will be how much? Exponent part is 7. 2 power exponent, that is 7. And what is the mantissa part? Okay, the fractional part. What is the mantissa part? Okay, the remaining bits you have to copy here. That is 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1. Okay, keep understanding. Hai na? Now what is important is, okay, how many bits actually to be taken for exponent, how many bits to be taken for mantissa, everything will be fixed. Okay, everything will be fixed. Through what? Through the IEEE standard, IEEE 754 standard for the representation of floating point numbers. And I told you there are two. One is single precision, one is double precision. Single precision representation is of 32 bits, double precision representation is for 64 bits. As I told you, na, like lesser the number of digits you take after the radix point. जैसे यहाँ पे मैंने लिया था only 2 digits. Okay, so there is loss of precision. That means more the number of digits या bits, binary में bits बोलेंगे. More the number of bits you consider, more the number of bits you consider, more will be the precision. Okay, so there are two formats, single precision representation and the double precision representation. Okay, एक है 32 bit का, एक है 64 bit का. Okay, now let us learn both. Although if I tell you with gate point of view या even engineering services point of view, question जो है single precision पे ज़्यादा आएगा. The question are expected more on the single precision. Okay, but yeah, let me cover up both. So single precision representation. Okay. Sine, of course, always will be 1 bit only, but in single precision, there will be an exponent of 8 bit. So 1 plus 8, 9, remaining 23 bits of mantissa. Remaining 23 bits of mantissa. Okay, and this is how we represent the number. Okay, sine, exponent, this is not the true exponent, this is E dash. I will tell you what this E dash is. ये यहाँ पे E dash आ रहा है. What is this E dash? I will tell you, just wait for that. Okay, so there is the sine bit, starting with sine, then comes the exponent part, that is 8 bit, so 30 to 23 bit number, and then remaining bit number 22 se bit number 0. These total 23 bits, this is mantissa. Okay, this is what is mantissa. This is the single precision representation. Okay, on the other hand, if I come to double, sine bit always will be 1. Exponent here in double precision is 11, and higher number of bits, more number of bits are allotted to mantissa. I am telling you now, more, if you take the fractional part more and more containing more number of bits, there will be more accurate answer, more precision. So this is double precision. Okay, so the highest bit, 63rd, is sine bit. 62 to 52, these will be the 11 bits going to the E dash. Again, what is this E dash? 51 to 0 will be the mantissa part. Okay, so what is this E dash? Well, isko samajh leta hai, as I am telling you. Okay, so E is the actual exponent. Okay, like in the previous example, when I told you this one here, this is what is the actual exponent. But in the IEEE representation, rather than the actual exponent, we feed the E dash. And why do we feed? What we are achieving? Once I start giving the example, that you will understand why we are doing that. Okay, so ये देखेंगे आप यहाँ पे. Okay, let E is the actual exponent. So E dash is known as the E, that is the actual exponent plus bias. Okay, plus bias. Yeah, vice versa. What is the actual exponent? It is E dash minus bias, where bias is given by the value 2 raised to the power k minus 1, where k being the number of exponent bits. Okay, for example, single precision पे आ जाएंगे, तो we know that in single precision number of exponent bits is 8. In the single precision, number of exponent bits is 8. That means k is equal to 8. So what is the bias value? 2 raised to the power 8 minus 1, that is 127. Typo error hai. That is 127. 2 power 7 minus 1. Okay, 2 power 7 minus 1. Okay, the range of E dash is 1 to 254. That is the highest value of E dash will be 254, not 255. And the lowest one is going to be 1. The lowest one is going to be 1. Okay, and then the actual exponent kitna ho jayega? As I told you, what is the actual exponent? It is the E dash minus the bias. तो 1 minus 127 minus 126 and 254 minus 127 is 127. Acha, you must also remember the range here, because sometimes, you know, previously they have asked in GATE regarding even GATE 23 itself, there was a question. I'll tell you what is that question is based on the highest number that can be stored, and previously भी GATE में ऐसे question हो चुके हैं. Yeah, identifying some floating point numbers given, identifying the largest of them या smallest of them. So you should remember the range of E dash. Then E you can automatically calculate. The range of E dash is 1 से 254. Okay, or the range of actual exponent is minus 126 से 127. Okay, similarly for k equal to 11, double precision में there are 11 exponent bits. Bias will be 2 power 11 minus 1, that is 2 power 10, 1024 minus 1 is 1023. Okay, the range of E dash in that case will be 1 से 3838 and the true exponent will be minus 1022 से लेके plus नहीं, यहाँ पे तो कुछ error आ गया. That is going to be up to 127 only ना. This is again a typo error. Okay, this is again a typo error coming up. Minus 1022 से 1023 and this is going to be high. How much? Just a second. 11 exponent bits है ना. Where is the calculator? Just a second here. So since we have how many? We have the 11. ठीक है. So in binary, and then I convert, it should be, sorry, ये नहीं, this should be 2046 primarily. Correct, yeah, this should be 2046. Okay, sorry, there was a typo error coming up. Okay, so, okay, ये तो हो गया range. Okay, ये तो हो गया range. Now let us come to some example. Okay, let us understand with the help of question. Suppose you have a number. Consider the following representation of a number in IEEE 754 single precision floating point number. See, we'll talk about both the examples. Given a 32-bit floating point number, what is the decimal value? Yeah, given a decimal number, what will be its representation is in IEEE 754 single precision format. Okay, देखेंगे यहाँ पे. Okay, so what is the decimal value of the above representation? What is the decimal value of the above representation? Everybody pay attention. Okay, so let me write down this and separate out what are what bits. This is 1, 1, 0, 0, 0. ये हो गया exponent part ना. 1, 0, 0, 0, 0, 1. Okay, then 0, 1, 1, 0, 0 and all zeros. ठीक है. Now pay attention. Dear, what is this bit? This is sign bit, meaning it's a negative number. Whatever your answer is going to be negative. What is this value? Okay, this is the E dash. Okay, this is the E dash, biased exponent value. Okay, not the true exponent. And what is this part? Okay, this part is known as the mantissa part. This part is known as what? This part is known as the mantissa part. Now, what is the value of this E dash in decimal? Okay, because question मुझे बोला है, tell me the decimal value corresponding to this. Okay, sign is 1. So dear, if you take this E dash na, 1 0 0 0 0 1 binary, when you convert to decimal, what is the quickest way convert binary to decimal? You can use the GP also. देखो directly. Yeah, this is what? 2 power 0 1 and this is 2 power 7. Okay. Okay, so 2 power 7, that is 128. So 128 plus of 1, this is 129. Okay, so decimal mein aa gaya. This is the E dash. This is the E dash. So what is the true exponent value? True exponent value is E dash minus bias. Acha, what is the value of bias? Okay, 32-bit mein, if you want, you can remember, or you can calculate again 2 power k minus 1 and it's a 32-bit single precision format. Okay, see, either they, what they have mentioned, single precision bola hai, so you should know that is 32-bit. Okay, and in the 32-bit format, exponent bits are 8. Okay, so 2 की power 8 minus 1, so 2 power 7, 128 minus 1. So the value of bias is 127. So what is the true exponent? Okay, whatever is obtained here, minus 127. So the true exponent value is equal to how much? The true exponent value is equal to 2. Okay, now let us focus on the mantissa part here. What is the mantissa part? 0, 1, 1 and rest zeros. Acha. Now mantissa means the fractional part. Okay, you know how to convert binary to decimal? You know how to convert any base to decimal? Okay, तो यहाँ पे when you are going to write down the position, because it is the fractional part, the positions will be allotted negative, -1, -2, -3, -4, etc. Okay, this is what is going to be the positions, and in general it goes up to -23, because there are how many bits of mantissa in single precision format? There are 23 bits of mantissa. Okay, so what is going to be this mantissa value when you convert this? Okay, so 0 wala to nahi aayega, only 2 power -2 will come and 2 की power -3 will come. Okay, 2 power -2, 1 by 2, 0.25, and 1 by 8, 0.125. Total answer is 0.375. 0.375. ठीक है? But as I taught you, this is what? This is the normalized value. This is the normalized fraction. Okay, this is the normalized fraction. So what is the actual fraction part? What is the actual fractional part? It is 1 plus the normalized value, no? That means it is 1.375. It is known as the 1.375. So now what is my answer? Dekho dear, pay attention. My number is positive or negative? Sign is 1. Okay, that means negative number. Sign is 1. Okay, so negative of, what is the actual fractional part? 1.375. Okay, how do we write down the number? Fractional part into r power e. Base 2 chal raha hai yahan pe. Okay, this is the fractional part into r. Okay, into r, that is 2, base 2, raised to the power exponent. What is the exponent value? 2. Okay, so 1.375 into the 4. 1.375 into 2 power 2, that is 4, 5.5. This number in decimal is, it is negative 5.5. In decimal, it is negative 5.5. That means, given any such question, okay, what is the final answer you are going to represent? Your answer is of the format plus or minus. Okay, plus or minus, that depends on whatever is the sign bit. So, dekho, I will write it something like this: -1 raised to the power sign bit. Understand? -1 raised to the power sign bit. Now, what is the meaning of this? -1 power sign. So, dear, if sign bit is 0, okay, -1 power 0 will be +1. So, it will be automatically positive. If sign bit is 1, so -1 power 1 will be negative. And that's what I want. Na? Negative पे minus लिखना पड़ेगा. Into what? Into what came up is, okay, 1 point, this is, see, from the IEEE format, what you get is the fraction, normalized fraction. Okay, then you add 1 to it. So 1.375 becomes 1.375. So in general, let me call it as 1.f. So whatever is the fractional part coming up, now write down 1.f into 2 raised to the power exponent value, the actual exponent, which is E dash minus Byjus, that you can calculate. Remember this. Remember this. And if you can remember this, let's attempt another question here. Let's attempt another question here. Come on, everybody, take up this next question. Okay, 1 0 1 1 1 1 0 0 0 0 0 0 0 0 0. Last may you see a 1. Okay. Come on, everybody. Come on, everybody. Okay. So let me write down. Let me copy this number here. 1 0 1 1 1 1 0, then 0 0 0 0, etc., 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 up to 1. Okay, then we know that this is the sign bit, this is the biased exponent E dash part, and this is the mantissa part. Sign bit is again 1 here, meaning that there is a negative number. Okay, now what is the value of the E dash? E dash is 0 1 1 1 1 0. This is binary. Converting to decimal. Okay, converting to decimal. Again applying the GP method. Ye ho gaya 0. Okay, sorry, this is 0. Then 2 power 1. Okay, that is 2. Then 4, 8, 16, 32 and 64. We stop here. This is the decimal value. Okay, so 96, 100, 116, 126. Just check out, it should be 126 in decimal. It should be how much? 126 in decimal, right? So what is going to be the actual exponent value? It is known as the E dash minus Byjus. Okay, 126 minus Byjus. Now Byjus in IEEE. Now we can remember now what is the Byjus? 127. Okay, so the actual exponent value is minus of 1. Minus of 1. Okay, of course that's in decimal. Now let's focus next on the mantissa part. Okay, so what is the mantissa part given to me? The mantissa part is 0 0 0 0 0 0 0 etc. up to 0 1. Correct, ये हो गया mantissa part. Okay, now again if I write down the positions, we know that because mantissa represents the fractional part, position will start from minus 1, minus 2 and it goes up to minus 23. So what is this mantissa value actually? What is this mantissa value actually? This is going to be 1 into 1 into 2 की power minus 23. Okay, this is known as the 1 into 2 की power minus 23. Okay, so we can calculate whatever this value turns out to be. चलो निकाल लेते हैं इसको. Okay, this is coming to be a very small 2 की power minus 23 आएगा. हाँ, correct. There is only 2 की power minus 23. So it's going to be a very small value. Okay, but whatever it is, then we add 1 to it. ये भी याद रखना. Okay, so this is if you convert this to decimal. Okay, and then directly if you add 1 point something 009. ठीक है, तो there will be some value coming up. ठीक है, last में लिखते हैं आंसर को. Okay, because we have to anyways multiply also ना, तो final multiplication के बाद आंसर लिखेंगे. So what is my answer now? As I told you, answer will be minus 1 raised to the power sign into 1 point m या 1 point f. Okay, into 2 raised to the power exponent. Okay, now let us feed the values. That is minus 1 raised to the power 1. Sign bit 1 है. 1 point f मतलब 1 plus 2 की power minus 23. Okay, and multiplied by 2 की power minus 1. Yeah, that is divide by 2. Okay, so yeah, finally when I divide by 2 also, so what is the complete answer I am getting? It's negative, okay, of 0.5 1 2 3 4 5 6 2 3 4 5 6 5 9. Okay, 0.50000059. Okay, that is the final decimal number. That is what is the final decimal number. Okay ji, that is what is given to you as the final decimal number. Done. Any doubts, please keep asking me. Done. Next question. Okay, next question. 0 1 0 0 0 0 1 1 1 1 1 0 0 1 0 0 0 till end it is 0. Till the end it is 0 only. ठीक है. Yeah, come on, everybody please solve and try to get the answer. Chalo. So this time sign bit 0 meaning it's a positive number. Okay, then this is the E dash value. This is what is mantissa. 10000 8 bit. Okay, so what is that E dash value, dear? This E dash value is 10000 0011. That's the binary format. So what is the value in decimal? Okay, so 1 plus 2 and directly 2 power 7, 128. Okay, so this is 131. 131 is the exponent value. Okay, Byjus the exponent value. So what is the true exponent? Again, just subtract 127. Okay, so the true exponent value here will be 4. Correct? Okay, so whatever is the fractional part we obtain, we are going to multiply it by 2 की power 4. Okay, now what is the mantissa part? Okay, 1001 and rest 0. 1001 rest is 0. Again, let me write down the positions for you. Minus 1, minus 2, minus 3, minus 4 up to minus 23. Okay, so what is going to be the mantissa? 2 की power minus 1 will come, 2 की power minus 4 will come. Okay, so how much is this when I add it na? 0.5 and 1 by, that is like 1 by 16. So 0.5625. Okay, now what should be my answer, dear? What is the answer format? Direct ways I have told you. Now what is the answer format? Okay, minus 1 raised to the power sign bit, okay, into 1 point f into 2 raised to the power exponent. Okay, so hence my answer is going to be minus 1 ki power 0, 1 point f, that is 1.5625 into 2 ki power how much? 4, that is 16. So when you multiply this by 16, answer is 25 and minus 1 power 0, so that is positive only, no? So answer is plus 25. This is the IEEE representation of the number plus 25. Clear? This is the IEEE representation of the number, that is the plus 25. Right? Okay, ji. Next question. The value of a float type variable is represented using the single precision 32-bit point floating format of IEEE 754. Okay, so 32-bit floating point format of IEEE 754. The float variable x is assigned a decimal value of 25.25. Like previous answer was 25. Okay, this is assigned a value of 25.25. This is assigned what? This is assigned a value of 25.25. Okay. How to solve this? 25.25. इसको कैसे सॉल्व करेंगे? ना मतलब दिस इज जस्ट रिवर्स. ओके, नथिंग. देखो हमें क्या करना है, वी हैव द प्लस 25.25. आई टेल यू द सिंपल वे. ओके, integral part, fractional part. Like remember decimal to binary, when you are converting na decimal to binary, how do you do? Okay, you have the separate rules for the fractional part, you have the separate rules for the integral part. Okay, so जो integral part है, that is 25. Okay, acha, how much is this in binary? 25 is a small number, na? 16 plus 9. 9 is 1001. Okay, so 1, then 1 and 1001. Okay, this is the binary value. Okay, now what is the fractional part? Fractional part is 0.25. अच्छा, 0.25 अगर है, what is the conversion, dear? We know this ना? कैसे करते हैं? Okay, how do you convert fractional part into binary? Multiplication table. तो 0.25 into 2. Okay, is 0.5. The integral part 0, fractional part 0.5. Okay, then what is the new fractional part? Keep multiplying by 2 till you get the fractional part 0. Okay, so this is 1. Okay, 1 means integral part 1 and there is no fractional part. And when the fractional part is 0, stop, and the answer is obtained by reading the integers in the regular order. Okay, so 0, 1. So this is how much? This is 0.01 in binary. This is how much? This is simply 0.01 in binary. इसमें कुछ नहीं है, correct है? This is simply 0.01 in the binary, right? 0.01 in the binary. Now dear, what to do? Okay, now dear, what to do? That means the complete number, if I want to represent, okay, let's go back here. When I want to represent the complete number, कहाँ गया? 25.25. when I want to represent this into binary, ये तो regular हो गया, like regular decimal to binary conversion. This is 11001, 11001. 0.01 in binary. But now comes the standard. How many fractional digits you need? Okay, sorry, how many digits you need before the radix point? How many digits you need before the radix point? सबसे पहले वो कर लेंगे. तो I need only 1 before the radix point. Okay, तो ये हो जाएगा. This has to be shifted here. Okay, तो 1, 2, 3, 4 places का jump. This already we have seen earlier. तो 100101, 1.100101. Okay. Now 100101 into, you have shifted the 0.4 places before, so you have to multiply by 2 ki power 4. Since it is binary, if it was decimal, we multiply by 10 ki power 4. So you have to multiply by 2 ki power 4. Okay, so if you multiply by 2 ki power 4, you get the exponent part also. Okay, how much is the exponent part? Then to represent into IEEE format, we need the biased exponent. वो भी निकालेंगे. How much is the exponent part and how much is the mantissa part? Both is obtained, ना? Both is obtained. What is the mantissa part? देखो, exponent part. Exponent is 4. So dear, what is the biased exponent? Okay, the biased exponent is E plus bias. Okay, E plus bias. Okay, so that is going to be 4 plus 8-bit फॉर्मेट में बायस इज 127 ना, 32-bit format but exponent is 8-bit. Byjus value 121, so it is 127 plus 4, 131. 131 in binary. In binary 127 plus 4 या 128 plus 3 करते हैं, तो 128 is 1 and 1 2 3 4 5 6 7 2 3 4 5 6 7. This is 128 plus 3 and 3 means end में 1 1 आ जाना चाहिए. Okay, so this is the E dash value. This is the E dash value. So what is your answer then? Okay, what is your answer then? What is the sign bit? I have taken only plus number na? Yeah, it's a positive number. Okay, देखो sign bit is 0 because it's a positive number. वो मैं यहीं पे बोल देता हूँ. Sign bit is 0. Okay, E dash is obtained. Okay, and what is this? This part is the mantissa part. Whatever is the extra bits, you will fill it with 0. So let me write down the answer then directly. Answer, sign bit 0. Then copy the E dash. Next क्या आता है? E dash आता है ना 100000011. And next क्या आएगा? Mantissa part 100101. 1000101000000. अच्छा, कितने zeros आएंगे? Okay, this is 6. Mantissa is 23 bits. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. This is the answer. This is the answer. Exponent, sign, E dash, mantissa. This is the answer. This is the 32-bit answer. Got it everybody how to do? If you have got this, let me know this answer then. Come on everybody. अगर ये आ गया तो quickly tell me the next answer everybody. चलो. You can try out this next one quickly everybody. Okay, so same type of question, decimal to 32-bit floating point में convert करना है, but the value is minus 14.25. Okay, so sign bit here will be 1. Okay, sign bit here will be 1. Now we need to convert 14.25. देखो, how much is 14? 14 is simple 1110, and how much is 0.25? 0.25 same value ना, तो last example से ले लेंगे. Why to do that multiplication table again? 0.25 is 0.01. Okay, so this 14.25, this 14.25 is 1110.01. 1110.01. Okay, 1110.01. ठीक है, so 1110.01 I have to shift this 3 places before ना. Okay, so 1.11001. 11001, and because I have shifted the point 3 places before, so I have to multiply by r power 3, 2 power 3, binary number है ना, तो multiply by 2 की power 3. So what comes out to be your exponent value is 3 then. ठीक है, and ये हो गया आपका mantissa वाला part. ये हो गया mantissa वाला part. अच्छा, now exponent value पे आ जाएंगे. So what is the E dash? It is E plus Byjus value. Okay, what is the actual exponent? 3 plus Byjus 127. It is 130. 130 is nothing. 128 plus 2. तो 1, 1, 2, 3, 4, 5, 6, 7. This is 128 plus 2 करेंगे तो यहाँ पे 1 आ जाना चाहिए. तो 100000010. This is known as the 100000010. So what is my answer now? Okay, I am in a direct position to write down the answer. Sign bit भी आ गया. Sign bit is 1. Okay, this is the sign bit. Then I will write down the E dash 100000010. This is my E dash. What is my mantissa part? 11001, 11001, but mantissa should be 23 bits. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 zeros, 11001 and 18 zeros. ठीक है, this is your answer. Okay, so we are able to convert whether floating point to decimal or decimal to floating point. We are able to do both. Okay, so let's go for the next question. Acha, yeah, what is this? Please focus now. Consider 3 registers R1, R2, R3 that store the number in IEEE 754 single precision floating point format. IEEE 7. See, most of the questions will only mention this much. So you should know what is that IEEE 75432, a single precision format. In that single precision, how many bits? 32 bits. How many for exponent? How many mantissa? This must be known to you. Okay. Assume that the R1, R2 contain the values hexadecimal mein given hai 4220000 something and C1200 respectively. If R3 is R1 by R2, divide karna hai. What is the value in R3? Okay, and of course division will be only feasible for you, only practically you can solve it in the decimal. That's the thing that you know easily. So हमें क्या करना है सबसे पहले? Let us start with the content of the register R1. The content of the register R1 is 4220000 and 0. Okay, this is 8-bit hexa, 8-digit hexa, and 1-digit hexa to binary कैसे करते हैं? Write down every hexa digit into 4-bit binary. Into 4-bit binary, तो 4 हो जाएगा 0100 00102, again 0010, that is 2, and then remaining all zeros. Okay, this is what is the binary conversion. Okay, now rest is what you are doing earlier. Rest is the same procedure जो अभी तक कर रहे थे. Okay, so क्या कर रहे थे? This goes to your sign bit. Okay, this goes to your sign bit. That means it's a positive number. Okay, this is your 100000100 8-bit. This is the biased exponent, and this is what is your mantissa part. Okay, so what is the biased exponent value? Okay, biased exponent value directly decimal में लिखेंगे ना, तो 124 plus 128. So biased exponent is 132. What is the mantissa part? Okay, we know that the position -1, -2, so directly only -2 position is coming. 2 की power -2. Okay, that is 1/4, 0.25. We can write down directly ना. Detailed में तो मैंने explain कर दिया. Now you should able to write down quickly. Okay, so what is this number equivalent to? Okay, this number is then equivalent to how much? As I told you. Okay, it's a plus number. Okay, then 1.25. Okay, 1.25, 1 point f. Okay, multiplied by 2 raised to the power how much? 132 minus 127. The actual exponent. This is the e dash na. Okay, that is 2 की power 5. Okay, that is 2 की power 5. चलो बाद में multiply कर लेंगे. 1.25 into 2 raised to the power 5. Don't multiply right now, because in whatever the next answer you will get, that will also be having 2 power some exponent. So एक साथ में divide करेंगे. You know. Now similarly, let us go to the R2 register. The R2 register contains the value C12 00000. Okay, that is hexa. Okay, convert this to binary. So C is 1100, then 0001, that is 1, 2 is 0010, and then all zeros. And then all zeros. So dear, this is your sign bit. Okay, this time it's negative. Sign bit indicating it's a negative number. 1000010. This is 8-bit. Count karna always. 8-bit E dash. Remaining mantissa. Remaining mantissa. Mantissa looks like same. 2 की power -2. Position -1, -2. So that is 0.25. That is a 0.25. केवल E dash आया. So what is the value of E dash? 12. Then directly 128. So E dash is 130. Okay. So what is this number equivalent to? Negative of minus a negative of 1.25. Actual fraction is 1.25. 0.25 is the normalized fraction. Okay. Into 2 raised to the power. Okay, 130 minus 127, the actual exponent. So negative of 1.25 into 2 raised to the power 3. Now what is the R3 is R1 by R2. Next बोला है the contents of R3 is R1 by R2. है ना 1/2 है? Yes, R1 by R2. Now what is the R1? That is positive 1.25 into 2 raised to the power 5. This is negative 1.25. So we have the same fractional part into 2 की power 3. So plus a ratio of positive and negative number will be negative. 1.25 cancel. Only what is left is 2 की power 2. Minus of, I will write it like this. Minus of 2 की power 2. Yeah, this is equal to minus of 1.0 into 2 की power 2. Into 2 की power 2. Clear everybody? Okay, now this means that your sign bit is 1. Okay, your actual exponent is 2. This is the actual exponent, and your mantissa part will be only filled with zeros. Your mantissa part will be only, because that is the actual fraction 1.0. So what is a normalized fraction? 0.0. Okay, so all bits will be 0. Acha, so what is going to be the E dash? It is 2 plus 127, that is 129. ठीक है, 129 को बाइनरी में कन्वर्ट करेंगे, 128 plus 1, तो 100000000, this is 128, add 1 here last में. Okay, so what is my answer? My R3 should be equal to, साइन बिट से स्टार्ट करेंगे, then exponent value 100000001, and then the mantissa value. Okay, now we have to write down the answer. Of course hex में given है, let us write down the answer in hex only. Okay, this is the binary answer. Okay, if the options are in binary. Okay, but data hex में तो option भी hex में ही आएंगे. This is C, 0000 is 0. Okay, 10000 is 8, rest is all zeros. 5 zeros will be there. So the answer in hexa will be C08, 00000. It should be C08 00000 in the hexa world. Looks fine. C08 00000 in the hexa world. Okay, hope you have understood the answer and solution. Next question की तरफ चलेंगे. Yeah, अच्छा, हाँ, this is what is the question I was referring to. Guys, this is GATE 2024, current year question only. GATE 2024. Choose the largest among all. Choose the largest among all. Okay, there's a 32-bit single precision format. Choose the largest among all. देखो, largest among all. देखो, सभी का साइन बिट 0 है. सभी का साइन बिट 0 है. So all are positive numbers. All are positive numbers. Okay. Now here the mantissa part is 0. In this, the mantissa part is 0. Okay, but here in all these three, mantissa part will be 2 power minus 1. All bits are 1, plus 2 power minus 2 up to 2 ki power minus 23. Who is asking you to calculate? You have to just say the largest. So definitely this mantissa is greater than 0. So option number A cannot be largest. So whatever is largest, that is among B, C, D, and all are of same sign. Okay, so now you have to compare with the exponent. How do you write down the answer? How do you write down the answer? Minus 1. Okay, all our answers positive only. Minus 1 power 0. So plus 1 point fractional part into 2 raised to the power exponent. 2 raised to the power exponent. Okay, where the actual exponent is E dash minus bias. Okay, bias hota hai 127 ka. Okay, now these three options have the same fractional. Okay, okay. This have the same mantissa. So answer will be highest for E dash highest. Answer will be highest if E is highest. Okay, so dekho B, C, D. Okay, they have the same mantissa. They have the same mantissa. Okay. So if you want to choose the largest number, that will correspond to largest E dash. That will correspond to largest E dash. Now what is the largest E dash? Definitely B not, क्योंकि B का MSB 1 है. C and D starts with MSB 1. B का MSB 0 है. तो out of C and D. Out of C and D. Okay. Definitely largest. B is not the largest. Now what about C and D? 11111110 या 11111111. देखो C is 11111110, D is 11111111. और अगर B को भी लिखना है, so what is that B? B is 0111111. Okay, ये तो wrong हो गया because यही नंबर छोटा है ना. Okay, out of C or D? Out of C or D, now you might be thinking D is the largest. You might be thinking D is the largest. देखो all bits 1. Okay, this is 255. Okay, this is one position before 254. You might be thinking as per the largest answer is D, but let me tell you what I told you. What is the range for the E dash? What is the range for E dash? E dash is from 1 to 254. Okay, so this is invalid. This is invalid. Okay, this is invalid exponent. ये तो नंबर ही invalid है in the IEEE 754 format. Okay, so what is the correct answer? It is C. What is the correct answer? It is C. Option number C. What is the correct option? Now that's what, Ramji, it's not D. Looks like numerically D is largest, but that is not the allowed value of E dash, na? That is not the allowed value of E dash. Okay, because if you take that as the E dash, that is 255, the actual exponent will be 128, whereas our actual exponent is 127, minus 126 and 127. That is the range of actual exponent, na? That is the range of actual exponent, highest up to 127. Okay, highest up to 127. That is the highest exponent allowed. Done, Eji? Okay, so this is what is the answer. Okay, so such questions, you know, what are the variety of questions like division ho sakta hai, choosing the largest, या converting floating point to decimal, या decimal to floating point, all that things we have been discussing. Okay, yeah guys, we are done. And also let me keep you updated that for your GATE 25 preparation on our Byjus exam prep app, the Ground Zero series, okay, to enhance your concepts from the ground level, okay, let's, you know, learn from zero level and take you towards a level where everything for GATE and ECE becomes easy for you. Okay, so that is the intention of Ground Zero series, live on the app. You can, you know, just download the app from the Google Play Store, or you can directly go to the description of this video. You will be finding the link to download the app there. And also guys, the complete courses for GATE 2000 and 2025 and 26, GATE and GATE plus engineering services, all courses available, English and Hindi, both the formats available. So you can choose even the language of your comfort, where you feel more comfortable. And these classes will offer you live classes, recorded lectures, study material, mock tests, practice quizzes, everything to make you exam ready under one umbrella. To know more about the courses, any more doubts you have regarding to the courses, the fees, timing, faculty, anything, you can contact 9241333666. Or you can fill up the basic counseling form. Okay, you can fill up the basic counseling form. It's available in the description of the video. It just takes few seconds. Fill it up, and you know, you're automatically slot with our expert counselor for one-to-one counseling, and complete guidance will be booked. Right. Okay ji. Chalo. That's it guys. You can also be connected with me in my Telegram for doubt discussions, for update about my classes, for updates about GATE and PSU notifications. That's it. And I think you enjoyed this video. Okay, you know, I'll tell you this video is sufficient for, you know, questions of GATE and ECE or any technical exam along floating point, whether you're from ECE or computer science or EE. EE mein GATE mein nahi hai directly, but in other exams it can be expected for EE. But for CSE and ECE it is anyways an important topic, and I hope this video will help you conquering your concepts for this topic. Yeah, definitely once the notification Divya for ISRO is out, we'll plan ISRO batches and ISRO classes as well. Alright, this is Rakesh Talreja signing off. Bye bye. Thank you. Stay safe and take care of yourself.